Calculus, video 76, U substitution with definite integrals. Okay, we've been doing U substitution with indefinite integrals, right? Integrals without bounds. Now we're looking at doing U substitution with definite integrals, ones with bounds. And so the question is, okay, what changes? What stays the same with U substitution? What changes when we go into definite integrals? So part of what we'll be learning is changing bounds as a part of learning this U substitution. So let's just start with an example here. Let's look at the integral from 0 to 3 of x square root 9 minus x squared dx. And let's go ahead and draw a picture of this first example here. So example 1. Okay, this is the square root, the function square root 9 minus x squared times x, or x times square root 9 minus x squared, looks something like this. The square root of 9 minus x squared, that'd be a semicircle, right? Without the x in front, that'd be a semicircle. With the x in front, it takes it any x values that are negative. It pulls the graph down negative. At 0, it's 0, and then the graphs for positive x values are positive. And so you end up with something that looks like this. This is f of x equals x square root 9 minus x squared. And what we're looking for is the area under the curve from 0 to 3. So basically we're looking for this area right here, that section. All right, we're still going to use the fundamental theorem of calculus, where we take the integral and we do capital F of b minus capital F of a. That's still happening. The problem is the integral we have, 0 to 3 of x squared of 9 minus x squared dx, is not an integral that we can just do this. You can't just simply, take the integral of x and call that x squared over 2, and the integral of square root of 9 minus x squared and call that whatever that would be, right? Those are two terms being multiplied, and you can't simply take the integral of them separately. What we need to be able to do is we need to be able to simplify this function before we take the integral. And that's where U substitution comes in, right? U substitution is a way to simplify the function before integrating. And so often what we're looking for is to let U equal a function whose derivative is also in the problem. So in this case, let's let U equal 9 minus x squared. Okay, I'm picking 9 minus x squared for a couple of reasons. One, its derivative is negative 2x, which I have the x in the problem, and so the x in the problem and the negative 2x derivative, that's going to cancel out. Secondly, the U is a lot of times the part that's inside the parentheses. In this case, it's inside the square root. The square root of 9 minus x squared, that's the same thing as parentheses 9 minus x squared to the 1/2 power. Oops, x squared to the 1/2 power. That's the same thing as the square root of x, square root of 9 minus x squared. So it's a lot of times the U is what's inside that parentheses raised to a power. Not always, but it's kind of a good place to start looking. Okay, so we're going to let U equal 9 minus x squared. Then, just like before, when we were doing U substitution with indefinite integrals, we say du is equal to the derivative of 9 minus x squared, that is negative 2x, times dx, our differential form. And then I like to solve for dx, divide both sides by negative 2x, and I get dx is equal to du over negative 2x. Okay, and then I'm going to do the U substitution just like I had with my indefinite integral, right? Except I'm going to change the bounds here in just a minute. For right now, I'm just going to leave empty bounds. I'll put the bounds back in. We're not getting rid of the bounds or anything like that. I want to change the bounds. So this is equal to. I just don't want to put them in yet. We'll discuss what they'll be in just a second. So we have x, the 9 minus x squared. The square root of that becomes square root of u. and dx becomes du, so times du over negative 2x. We see that the x's cancel. We can bring that negative 2 in the denominator out as a negative 1/2 power. And bring the negative 1/2 out, then we have square root of u du. Okay. But no longer can I use the bounds 0 to 3. The reason is the bounds 0 to 3 are x bounds. These bounds 0 to 3, those are x bounds. X bounds. They are bounds on the x-axis, right? This is the x-axis, this is the y-axis. They are bounds on the x-axis. They are actually x values, from the x value of 0 to the x value of 3. But now that we have done a u substitution, we no longer have x's. We have u's. And so I can't use the same bounds. I can't use the bound from x equals 0 to x equals 3 because I have u's, not x's anymore. In fact, what we've done here is a transformation. By letting u equal 9 minus x squared, we have performed a transformation to where we're no longer having an xy coordinate system. Now we have a uy coordinate system. Okay, we're not going to have x bounds anymore. We are now going to have u bounds. We've changed the graph from an xy coordinate system to a uy coordinate system, and the transformation to go from x's to u's follows this let u equal 9 minus x squared. That is what is happening. That's the transformation from x's to u's. So what we need now are u bounds. But as we go from x's to u's, the function it's not even the same anymore. We used to have a function f of x is equal to x times the square root of 9 minus x squared. But now look at our function. Now our function is negative 1/2 square root of u. Right? That's a completely different function, which is then going to have completely different bounds. So here's how you change the bounds. So I'm going to put another box over here called bounds. And I'm going to have an upper bound of 3 and a lower bound of 0 for the x's. And so for an upper bound of 3, I like to do my upper bound up top so I don't mess these up. For an upper bound of 3, for x equals 3, what you do is u is then equal to, you simply plug 3 in for the x value in this let u equal 9 minus x squared. So we're letting 3 equal x. That would be 9 minus 9, that becomes 0. So my upper bound of x equals 3 becomes an upper bound of u equals 0. So we get an upper bound of u equals 0 up here, and also here. For my lower bound, which started out x equals 0, and in the u bounds, in the u world, if you will, we get u equals 9 minus, again we let x equals 0 this time, 9 minus 0 squared, which is 9. So my lower bound of x equals 0 now becomes a lower bound of u equals 9. A couple of things to note here. One, notice that we went from 0 to 3, right? 3 being bigger than 0. But because the 3 went to 0, the upper bound of 0 is 0 for u's, and the lower bound is 9. We don't automatically say, okay, 9's bigger than 0, therefore 9 is on top, right? Because 3 was on top, and it went to 0, then the 0 is the upper bound. Because x equals 0 is the lower bound, and it went to 9, then 9 is the lower bound. However, when we go over here to this portion right here, we have negative 1/2 times the integral from 9 to 0 of square root of u du. Convention says we typically have a lower bound that is less than our upper bound. So we're going to switch those. Instead of going from 9 to 0, lower bound 9, upper bound 0, we're going to go from 0 to 9. And when we do so, remember that creates a negative. And so we already have a negative 1/2 out front here, so that's going to be a negative 1/2, or just a positive 1/2. And so this is equal to positive 1/2 integral from 0 to 9, switching those bounds. Instead of 9 to 0, now it's 0 to 9, square du du. The picture of this looks like the graph of 1/2 square root of u. Right, so the function g of u is the graph 1/2 square root of u with u bounds from 0 to 9. So the u bounds on the curve 1/2 square root of u correspond 0 to 9. The interesting part about that is this area in green here for 1/2 square root of u from 0 to 9, even though the curve is different and the bounds are different, the area you're getting there is the same as the area that we get from 0 to 3 of x squared and 9 minus x squared. Those areas are the same. Curve's different, bounds are different because both experience a transformation of u equal 9 minus x squared. All x squareds could be plugged in there and get the u values for there. But under that transformation, we get this curve. Now, g of u is 1/2 square root of u, new bounds 0 to 9, different kind of region, but same area. Same area. So this area in green here happens to be the same as this area here. And it's not the best graph, but they are in fact the same area. So now we just do the fundamental term of calculus. We'll do the integral, we'll do f of b minus f of a. It looks something like this. Okay, this is equal to 1/2. The antiderivative or integral of square root of u, remember square root of u is u to the 1/2. So we're going to add 1 to that, that's u to the 3/2, divide by 3/2. Dividing by 3/2, that's the same thing as 2/3. Evaluating that from 0 to 9. So these are u bounds. These I didn't label those. The x bounds were from 0 to 3. The u bounds are 0 to 9. And so since these are u bounds, we can simply plug those u bounds into the u value. We don't have to turn this back into x's. All right, so we have, let's see, the 2's cancel here, so that would be 1/3 u to the 3/2 from 0 to 9. Plugging that in, I get 1/3 9 to the 3/2 minus 0 to the 3/2. That's 1/3 times, let's see, square root of 9 is 3, 3 cubed 27, 1/3 times 27, which is 9. Okay, so the area of both of those regions is 9. Again, notice, because we changed our bounds right here. X equals 3 went to 0, x equals 0 went to 9. We do not have to go back and replace this u with x's. I can simply plug the u bounds into the u. That would have been the same thing as plugging the x bounds in if we had x's. Or don't change the bounds. So I like changing the bounds. I like changing the bounds, and I'm done here. Once I get my integral, I plug those u bounds in, I get an answer, and I'm done. But you could have, instead of changing the bounds, go back and turn everything back into x's and keep your x bounds. So, for example, same problem. The first way here, method number 1 was changing bounds. Changing bounds. I like to change bounds. And as I'm working these problems on these videos, you'll see me changing the bounds when I'm doing the u substitution for definite integrals. But you don't have to. Not changing bounds. Let's work this same problem without changing bounds. We started off with the integral from 0 to 3 of x square root 9 minus x squared dx. we're still going to let u equal 9 minus x squared. Du then is negative 2x dx. Solving for dx, I get dx equals du over negative 2x. I'm not going to change the bounds this time. I'm going to leave my 0 to 3 bounds, those x bounds. I have x squared of u, and then dx becomes du over negative 2x. Dx is still cancel. I'm still going to pull out the negative 1/2. Integral, I'm going to leave my 0 to 3. This is u to the 1/2 du. And I'm going to integrate. Negative 1/2. U to the 3/2 times 2/3. Evaluated from 0 to 3. This is equal to negative 1/3. U to the 3/2 evaluated from 0 to 3. Now the reason I like to change my bounds is because I don't want to be tempted at this point to plug in 3 and plug in 0, like the first fundamental term of calculus, and have an answer, because that answer would be wrong. Right? If I plugged in 3 and plugged in 0, that would be wrong. And the reason it would be wrong is because these are x bounds. And I can't plug x bounds into u. I can't substitute x bounds in for u's. What I have to do if I don't change the bounds is go back and replace u with the 9 minus x squared. And so I have this. This is equal to negative 1/3. 9 minus x squared to the 3/2 power, evaluated from 0 to 3. Now I have x bounds and I have x's. Now I can do the fundamental term of calculus. I can replace this with 3 minus plugging in 0, and I get negative 1/3 times 9 minus 3 squared to the 3/2 minus 9 minus 0 squared to the 3/2. Right, plugging in the 3, plugging in a 0. That's negative 1/3. 3 squared is 9. 9 minus 9 is 0. So that's 0 to 3/2. That's 0. And then on the right side here, 9 minus 0 squared is 9. Square root of 9 is 3. 3 cubed is 27. And I get negative 1/3 times negative 27. That would be a positive 9. Same answer. Okay, same answer. But I know myself, and I know that I'll accidentally occasionally plug the 0 and 3 into the u without changing them back to x's first, so I take care of that right away. I like to change my bounds, and then I don't have to worry about it. Once I have the 0 and 9, I can plug those into the u, get an answer, and I'm done. However, if you like to not change your bounds, that's also perfectly fine. You cannot change your bounds. You can do the integration with u substitution. Just please make sure that you replace the u with, in this case, the 9 minus x squared before you substitute in the bounds. Okay. Personal recommendation here is pick one. Whichever one you think that you'll work best with, pick one and kind of stick with it. I think people get confused when they try to kind of mix and match. They want to change the bounds sometimes and not change the bounds the other time. So at least as we're learning this, like this first time, right, first go around learning the u substitution with definite integrals, pick one of the two methods and just kind of do that one only until you get used to it. All right, that's all for this video.